The gas chapters are divided into two, actually, two chapters. Yeah. First is introduction, and then the second is the ideal gas law, which we'll talk about later. These are the learning objectives that you have a whole bunch. Macroscopic, kinetic molecular theory. Let's read the learning objectives here. Well, let's just look at some basic observations for gases. A gas, you can fill a container here with a gas. One thing is you can try to compress the gas. So just put a disc here and some weights. Those weights will put some pressure on the gas. If we can compress the gas more, if we add an additional weight here, the volume will shrink. Or if we remove weight, the volume expands. And so what we say is for gases, the volume's not fixed. The volumes can contract or expand. So we talked a little bit about this later. In fact, we can pull this, and that creates vacuum, which is just a thinner and thinner gas. Pulling this here. And so, these are your observations, and then, we have observations, we look for patterns, and what do? We get observations, we look for patterns, and we try to come up with what? With laws. Eventually we want to understand those laws deeper, so we come up with a hypothesis and then theory. Well, chemistry is a multi-pronged thing. Obviously somebody's already come up with a theory underlying these. And so here are the observations. The theory underlying this is that these gases are comprised of tiny particles. These tiny particles are atoms or molecules, or even ions. If we're dealing with a plasma, we'll have ions. Do you know what ions are? You heard of the term ions? Yeah, they're going to have a charge on the atom. So it might be a positive, or even 2 positive charges or 3 positive charges, or negative charges. -1, -2. Those are common charges. In fact, we're going to start learning the names of some of these ions, which are very common. Ions are quite common, but in plasmas, the particles are charged. In the normal gas, the particles are neutral. In plasmas, the reason the particles are charged in the plasma is because of extreme kinetic energies, extreme temperatures. But anyway, this is kind of the theory. Now, the theory of this, it's all part of the theory of chemistry, but the theory of this, they gave a special name. It's called kinetic molecular theory. Kinetic, what does kinetic mean? Motion. What types of kinetic? There are 3 types of motion. What were the 3 types of motion? 3 types of motion. Yeah, translational, vibrational, rotational. So these particles themselves, they don't have to be spherical like this. They could be, different shapes depending on the molecule. How the atoms are put together in a molecule, like water. Water is not spherical like this. Water is kind of a boomerang type shape. But anyway, those can also have vibrational, rotational motion. But if we see little single atoms like this. If you see single atoms like this, there's no rotational, there's no vibrational. I mean, obviously atoms can rotate, but it's not really going to change the solutions. They're different, not different levels of motion. And then mainly translational motion. And so the way people visualize this in terms of theory is that, gases are comprised of atoms and molecules and lots of empty space. And so that they can be compressed and expanded without any trouble. So, jump ahead to theory. It's good to understand it from both perspectives, from observation, factual observations, and from a theoretical perspective. This is what I mean by the multi-pronged approach. We don't do strictly observational, and we don't strictly do theoretical. We do a mix. And the same thing here. When we look at different states of matter, a solid, is this crystalline or non-crystalline? Non-crystalline would be what? We call non-crystalline solids. We call non-crystalline solids. Amorphous, yeah. amorphous or glassy solids. It's hard to make glassy metals or amorphous metals. The metals are typically crystalline. People are trying to make glassy or amorphous metals because they might have different properties, unique properties that might be useful, but they're hard to make. Like regular glass like this is no problem. This Pyrex glass is easy to make amorphous. In fact, actually they don't show the structure of the glass. Here we have an iron nail. There's a bit of corrosion on the surface of that iron nail. But inside, a well-ordered arrangement of iron atoms. Here we have water. You know, iron, does it have vibrational motion? Solid iron?
Yes.
Does it have rotational motion? I mean, yeah, the atoms can rotate, but you know what we're looking at are different levels of rotation. You know, so not really. How about translational? Does iron have translational motion? No. And then here for water, what does water have? Does water have translational? Yeah. Vibrational? Yes. The water atoms, the atoms in water themselves can vibrate. In fact, water has, if you can believe this, water only has 3 vibrations that are allowed, you know, due to the theory. You know, the atoms can do something like this, and the atoms can do something like this, and the atoms can do something like this. And that's it, you know, for the hydrogen atoms and the oxygens. So there are 3 types of vibrations that we see for water molecules. It's based on the shape, something you can get from the theory. And then, obviously, there's translational and rotational. But even though there's translational, the water molecules are stuck together. It's like glued, you know, sticky. They're stuck together. Here in the gas, what kind of gas is that? That looks like what? Diatomic gas, for one. So it's probably what? You think it probably is? If it were hydrogen, I wouldn't expect it to sink. You know, hydrogen is very low density gas. You know, it has a much lower density than air, so hydrogen usually rises in air. So this looks like this is a gas that sinks in air. What would a gas that would sink in air be? Think about the diatomic gases. What would it be? I don't know. Or it could be there's just not much gas in here, and the balloon is a pretty thick walled balloon. So it's kind of heavy, so it could weigh it down. But anyway, we have a gas. So we see the macroscopic and we see the particulate level. This particulate level we try to visualize using kinetic molecular theory. You know, the motion. Kinetic means motion. Molecular is for molecules, motion of molecules. Not just molecules, but also atoms. But it would be cumbersome to say kinetic, atomic, molecular, ionic theory, something like that. Gases can form homogeneous mixtures easily, you know? So if you have this red gas here, it's easy to mix in some green gas here. There's no problem making mixtures like this. Like air, you know, air is a very homogeneous mixture. There's plenty of space, so you can just add more particles. One thing that's going to change, though, is the pressure. When we look at this, you know, the pressure, when we feel pressure, like air pressure, what you're feeling is you're feeling the collision of the air molecules on your hand or whatever else. You feel that air pressure. But here, when we look at the collisions here, there's three atoms that are going to collide with the wall. Now over here we have 1, 2, 3, 4, 5, 6. Now we've got 6 atoms colliding with the wall. What happens here is the pressure just doubled, you know, because we have twice as many atoms colliding with the wall of the container. And so, yes, we can form a mixture like this, but, you know, the pressure is going to have to increase here. Either the pressure increases, or what we do is we double the size of the container. If we double the size of the container, the pressure will maintain, you know, the same. And so it's not so, you know, you have to, you know, kind of force these green ones in here because of the pressure difference, you know, because we're working, you know what the pressure is that we're working with? You know, the normal everyday pressure in this room. You know, today the pressure, they say, is low, probably because the storm's moving in, so it's lower than normal. But when they say lower than normal, it's just a little bit lower than normal. But we'll talk about the air pressure in this room in a little bit. Well, one thing about pressure is this, and these PowerPoints aren't yet. You know, for gases, the pressure, if we put a pressure gauge, you know, one at the top of the container, two in the middle, one at the bottom, they're all going to register the same pressure. That is because gases, when they collide uniformly with the wall. I mean, these gas particles are moving quite fast. And since they're moving quite fast, you know, they're very very light, you know. A lot of people say, you know, what holds the particles down in the liquid? You know, what holds the particles down in liquid? Is it gravity? You know, if you look at this liquid, this liquid's at the bottom of the container, but a gas will fill the entire container uniformly, like a balloon. So is it gravity that holds the liquid down? It's not gravity. You know, what holds the liquid down is the surface of these particles are sticky, and they get stuck to each other. You know, some particles are more sticky than others. That stickiness is like some molasses or syrup or something like that. That stickiness is what we call intermolecular attractions, which we talked about before. Do you recall intermolecular attractions? This is what holds it. Otherwise, these particles are very light. If you take a look at a single atom is extremely light. You know? Gravitational forces are going to be pretty weak between such a light particle and the center of the Earth. And so it's not gravity that holds it, it's the stickiness of the surfaces of these that kind of get stuck together. These are less sticky, so they can break apart. They're more free. When we look at liquid pressures are going to depend on the depth. It's like a swimming pool. You know, the deeper you go in the swimming pool, right, the higher the pressure. And one way of thinking about pressure in a liquid sense is you got the weight, you know, the weight of all those water molecules on top of you. And so the deeper you go, you got more and more. Water is very heavy. If you pick up a gallon of water, it's not so light. And so if you're looking at a swimming pool and you're 8 feet deep in the swimming pool, that's a lot of water above you, a lot of pounds of water above you. And all those pounds are going to add up into higher pressure here. And so the liquid pressures depend on the depth. Whereas gas pressures do not depend on the depth, unless you're looking at, you know, like the atmosphere. In a typical lab, you have a container of gas. There's going to be no difference here. But if your lab was the whole Earth, then you're at sea level. You know, at sea level, the pressure is higher than at the top of the mountain or lower. You know, like if you're at sea level and you drive up to the top of the mountain, is the pressure going to be the same, higher or lower? The air pressure is going to be lower. Why? It's like swimming here, rather than, you know, in liquids you notice it rapidly. But in gases, you notice it gradually because of this. In liquid, you can easily feel the weight of the water, but you know, air, you don't necessarily feel it. But air, you would feel it. You know, let's say if this were some mountain here. And then we go all the way down to the ocean here. So this is the ocean here. And so we have sea level here. Sea level. And so obviously if you're swimming, you know, the deeper you swim under the water here, you know, the higher the pressure because you got all the weight of the water. But not only do you have the weight of the water, but you also have the weight of the air. And so you have the weight of the atmosphere on top plus the weight of the water that gives you the total pressure that you're experiencing down here. Do you know how much the atmosphere weighs at sea level? the atmosphere weighs, well, think about if you swam 30 feet underwater, think about all the water.
Is it 1 quart?
Well, I'm talking about how much it weighs in, let's say, it's not 1 torr, it's 760 torr, but what is a torr? We'll talk about that a little bit. But, okay, in order to have the same weight, if we're looking at the weight of the air here, or the atmosphere, we have this huge blanket of air that stretches out into space, right? And that huge blanket of air here would be equivalent to being about 30 feet underwater. And so if we're 30 feet underwater, we call that about 2 atmospheres of pressure. If we're at sea level, we call it 1 atmosphere of pressure. Atmosphere is a typical unit that we use to measure pressure. And so here, if we're at sea level here, we're experiencing about 1 atmosphere of pressure. Now, where does that 1 atmosphere of pressure come from? It comes from the weight of this blanket of air here. The weight of the blanket of air. And so the air is much thicker, air is much thicker near the sea level, and then as we go up, it thins out. This is due to gravitational, especially with the heavier molecules are going to sink because of gravity. And now gravity is going to play a bigger role here because we're looking at much larger distances. So up here, the weight of the atmosphere is much lower. So up here, like maybe at the top of Everest, we're looking at half an atmosphere or a third atmosphere or something. It's very low. We can calculate it actually. This is, we can figure out the weight of the atmosphere due to elevation empirically. What the empirical equation is? Empirical equation? Somebody? Well, I talk about empirical equations like when I talk about scientific method, like day 1 or something like that. You flip back, see if it's in your notes from day 1 or day 2.
Based on observation?
Yeah, just mathematical based on observation. Basically, what you see is an exponential decrease in the pressure as we go up with elevation. So this is a simple equation that we can use to predict what the pressure is at any elevation, basically, based on the weight of the atmosphere. Maybe I'm not going to show it. Well, anyway, let's just continue on here. And so it's just this weight of the air. And so when we have a small sample like this, then it doesn't really matter. The pressure is the same on all surfaces. But if we take a huge container like this, then gravity is going to play a role. And then at the top of this container, let's say the top of the container is at the top of Everest and the bottom of the container is at sea level, then you're going to see a difference in the pressure.
Did you want to take us to memorize the conversion factor for the atmospheres to like kilopascals and torr and stuff?
Some of them. Just a couple. We'll talk about that. Like chemistry, there's a logical progression here. Logical progression is observation to pattern to laws to hypothesis to theory, but the theory's already been worked out for this. Since the theory's already been worked out, we're doing the multi-pronged. We're going to look at theory at the same time as looking at observations, at the same time as looking at laws, and so here's the theory of this. And I call it kinetic molecular theory. This is a particular level explanation of laws. These are the basic features of this theory, that gases consist of molecules in empty space. This is not entirely molecules, and what else could it consist of? It doesn't have to be molecules. For example, if we're looking at helium gas, does helium form molecules? No, it's atoms. And so gases consist of molecules, atoms, or because it could have a combination of them. Well, molecules would be compounds. Compounds would be two or more atoms. And in this case, we have two types of compounds. Do you recall the two types of compounds we have? We had compounds that form molecules, and we had compounds that form, what did I call it? Started with an L. This is, lattices, right? And somebody in the afternoon asked me what the test is like. Is it, is the test, is there time, or is it, how much time do they have for the test? Is there time to review? Are there going to be too many problems to finish, time? And so it depends on the type of test. I'll tell you, most of the tests I took at UCLA were timed. You had a certain amount of time. If you didn't finish, that's fine, usually, because most people didn't finish because they put too many questions on there to finish in the allotted time. Right? Well, their speed makes a difference. Speed. How do you get that speed? How you get that speed is you just drill these down. Like, all the notes, like the next week's our test, day one, stuff from day one, the scientific method stuff, by now I would have read, and probably written over, I probably would have read that about 30 times by now. It would have been so ingrained in my memory that when the test came, it would just be so fast, because you had to be fast. You had to be fast in order to get the maximum number of points because, there's not enough time. But I told the student, this was yesterday, I told the student, no, I have a little bit different philosophy for my test. But I know I could be, I have mixed feelings about this because my philosophy is different than practically everybody else's. And my philosophy is to give you enough time to review, check your answers, punch them again in the calculator. Okay? Because I didn't like the speed thing. I had to get good at the speed thing because that's how the tests work. They rewarded that. And so this is why, I drilled it down. Scientific method, boom, I had that down because that happened the first week. By the time the midterm came, this is usually a midterm and a final. By the time the midterm came in the 5th week, it was down. I probably read it over 100 times. How many times have you read it by now? Maybe 0? Once from the initial and then 0 after that. It's not good. For speed. So those are the test taking skills I had to learn when I transferred. Otherwise, I wouldn't have survived. Well, anyway, let's continue on. Volume occupied by the molecules in a gas is negligible. In other words, gases are mostly empty space. This is what I always did. When I did my notes, I always rewrote them in my own words. Like the professor would say something, I wrote it down, tried to write it down word for word, and then redo what they said in my own words so I could remember it better. And so something like this, I definitely rewrite in my own words because I wouldn't like this. I would say gas is mostly empty space. Attractive forces among molecules of a gas are negligible. Now, this one, it's the stickiness of what I talked about. Those are the attractive forces. Obviously, gases they can't be too sticky, If they're too sticky, then the particles are going to get stuck together and we got a liquid. And so this is what this statement's saying. In order to be a gas, the particles can't be stuck together. And that stickiness increases for solids. It becomes so sticky they can't move anymore. For liquids, it's sticky, but at least they can still move. Solids are locked in place. Go on to the next one. Average kinetic energy of gas molecules is proportional. We talked about temperature. What happens when you decrease the temperature? What happens to motion? it slows down. Eventually it's going to stop. When it stops, we call that temperature absolute zero. Absolute zero, well, absolute zero is this. You know, let's talk about absolute zero right now, because then we can talk about temperature and gases a little bit. Absolute zero is defined as minus 273 Kelvin, or not, minus 273 degrees Celsius, sorry, which we have a new scale. This is minus 273. You can't go any colder than this. Like, for example, if you try to go to minus 274 degrees, it doesn't happen. You
Why?
can't. Why? Because it's like this. When motion stops, that's it. I mean, can it start going reverse? You know, what happens? Because when we feel temperature, we feel the motion. If something's very hot, there's a lot of motion. If it's very cold, there's very little motion. Now your hands, there's motion here, right? So if you touch a cold object, you know, you're increasing the motion of the cold object, decreasing the motion of your hand. And so once motion stops, because temperature and kinetic energy are related. And so temperature is directly proportional to the kinetic energy. Kinetic energy is the energy of the motion. We talk about kinetic energy and potential energy. And so once motion stops, then there's no motion, and temperature's got to be zero. This temperature is a measure of kinetic energy. Does that answer or not? I mean, what can you have? Can you have negative motion? Is there such thing?
Well, you said that, so you can't have, is that degrees centigrade? So,
It's impossible temperature. This is an impossible temperature.
if that's just my farthest reported cold life we've ever gotten.
No, this theory, the coldest it's gotten is above this. In theory, this is the coldest temperature. Nobody's achieved this temperature. It's too difficult. It's like a perfect vacuum. Nobody's achieved a perfect vacuum.
What's the lowest temperature we've achieved?
The lowest temperature is very close to this. Extremely close. Actually, you know, I don't know the number offhand. I know a number, but it's old. I think people have gotten even colder. And so that's a very interesting question. What is the coldest temperature achieved? We can take a look at that. Maybe on Wikipedia, it's probably not it. Well, in space, it is obviously very cold. This might be the natural temperature in the lab. I have to look it up. I don't know why it's not coming up with it. These are old. Well, 4.2 Kelvin is very easy to achieve. We'll talk about 4.2 Kelvin in just a second. But the temperatures are very close, and it's very close. And so minus 273, what is that in degrees Fahrenheit? Degrees Fahrenheit is equal to 9/5 degrees C. So this would be minus 273 degrees C plus 32 degrees. And so in Fahrenheit, what would that be? Take a look. And so it would be 9 times minus 273 divided by 5. Minus 459.4 degrees Fahrenheit. What we had. So this would be the coldest temperature possible with Fahrenheit. This is where all motion stops. And then Kelvin's easy. Kelvin is defined as 0 Kelvin. This is named after Lord Kelvin. And so this is called the absolute temperature scale. 1 Kelvin, you know, when we're looking at delta T, 1 Kelvin is equivalent to 1 degree C, which is equivalent to 1.8 degrees Fahrenheit. And so Kelvin unit is the same as Celsius unit, which is different than a Fahrenheit unit. And so, you know, when we look at the two temperature scales side by side, we'll have minus 273 Celsius, minus 459.4 degrees Fahrenheit, 0 Kelvin. And then we warm this up. There's some temperatures that you should have as reference points. 0 degrees C, you hit, let's write that here, 0 degrees C would be equivalent to 32 degrees Fahrenheit, which would be equivalent to 273 kelvins. And then 100 degrees C, this is not the scale, 100 degrees C would be equivalent to 212 degrees Fahrenheit, which is equivalent to 373 kelvin. So there's a very simple formula for temperature. Temperature in Kelvin is just equal to temperature in degrees C plus 273. Now Kelvin, we don't use the little degree symbol, we just write K. Now, the cold temperature that's easily achieved on Earth is 4 Kelvin. 4 Kelvin is easily achieved. 4 Kelvin is easily achieved because this turns out to be the boiling point of helium. It's liquid helium, though. And so what you have to do is you have to make liquid helium. If you make liquid helium is going to be at 4 Kelvin. And then you can cool things down to 4 Kelvin. Liquid nitrogen, have you heard of liquid nitrogen? Liquid nitrogen is a lot warmer. What is the temperature of liquid nitrogen? Well, it's the boiling point of nitrogen. So we just look up, liquid nitrogen. Minus 190 or so. Minus 195, 196C, 77 Kelvin. And so 4 Kelvin, this boiling point of helium, what is it, 77 Kelvin? 77 Kelvin would be liquid nitrogen. Call it liquid N2. And so both of these are cryogenic fluids. So both of these are used to cool things down. Liquid nitrogen and liquid helium. Anyway, let's continue on. When we're dealing with gases, we like to use the Kelvin temperature scale. That way there's no arbitrary zero. We call these arbitrary zeros. Like this zero here is kind of arbitrary. This is not an arbitrary zero. This was arbitrarily chosen. This 0 point was arbitrarily chosen as what? As the freezing point of water, right? The melting point of water, or ice. Now, this is arbitrary because what happens? If we have positive Celsius, are we moving left to right? And then once we go to negative, let's say I'm plus 10 degrees C. So I'm plus 10 degrees C. What happens if I go negative 10 degrees C? Do I go backwards, same speed? This is negative 10 degrees C. This is positive 10 degrees C. Yes? True? And so if I'm positive 10 degrees C, I'm moving left to right. If I'm negative 10 degrees C, I'm moving right to left. I go backwards. Does that seem to make sense? Yeah, it seems to make sense, but it's wrong. It's wrong because what it means is at 0 degrees C, does motion stop? No, that's why it's an arbitrary zero. What we have, At 10 degrees C, motion's like this. At minus 10 degrees C, it's exact same, but it's a little bit slower. There's nothing that changes in going from positive to negative other than we just go slower. That's why it's called an arbitrary zero. Whereas this is not an arbitrary zero because there's something that happens huge when we switch from positive to negative. There's something that happens that's huge is we can't go negative. It's impossible. Right? How about 0 Fahrenheit? Do you know how 0 Fahrenheit's defined? For a long time, I thought, because I never bothered looking it up, but for a long time I imagined Fahrenheit going outside, and it was a super cold day, the coldest winter day that he had experienced, and recorded the temperature and said, okay, I'm going to call this 0 because this is the coldest I've ever felt in my life. But how reproducible is that? You're going to make a thermometer. How reproducible? That's not very reproducible. You need something reproducible. And Lord Fahrenheit was a better scientist than that. And so, salt water? If you have salt water, you can make like ice cream. You throw it in the freezer. You can get temperatures lower than whatever. And still, it could be liquid too. In other words, it's like 0 degrees Fahrenheit. This is something I just learned not that long ago, but it's based on having some kind of brine solution, salt water, and then freezing it. And it's a very consistent temperature that they can hit 0 Fahrenheit each time. Anyway, that was it. Temperature scales. This is back to chapter 1. All right, here, molecules interact with one another and with the container walls without loss of kinetic energy. What this means is, usually when you have a collision, things slow down, but in gases they don't. And when things slow down, they tend to do something. This is what we call kinetic molecular theory for an ideal gas. We can take a look at the densities here. There's going to be a huge difference in density. The gases are about 1,000 times less density. And so, for example, if we have 1,000 molecules here, we have one molecule there. It's like 1,000 times less dense. So, just a figure trying to illustrate that. Typically 1,000 times. So do you know what the density of water, liquid water, is roughly? If I had a milliliter of water, do you know how much it weighs? It's an easy density to remember. It's not a... If you have a milliliter of water, it should be to the first blue line here. 1 milliliter of water weighs 1 gram. Is that exact or approximate? It's approximate. It's not exact. It's approximately 1 gram. It's actually to 3 sig figs, it's good. 1.00 grams. But if you go to 4 sig figs, it's not good. To 4 sig figs, it's like 0.9998, something like that. Depends on the temperature, because water, sometimes when things get warm, they expand a little bit. When they get cold, they contract a little bit due to the motion, due to the movement. Water is one of those. Water has a very unusual expansion and contraction behavior, because when water gets cold, rather than contracting like most things, when water gets cold, it expands. It expands because the sticky part of the water, we'll talk about that later, is very directional. There's an orientation to it, but you don't have to worry about that. Let's talk about pressure. Liquid pressures are different. Liquid is the weight of the air. Gas pressure is the weight of the gas. But there are different ways of thinking about the weight of the gas, because when you have air seems to be weightless, doesn't it? But it isn't weightless. Air is not weightless. And so one way of visualizing what's happening with pressure is the force of the collisions, you know, over some unit area. And so we got molecules, atoms, ions colliding with the wall of the container. And depending on how many collisions you have in a given area, that's going to give you. So if there's 0 collisions, what's the pressure? If you have 0 collisions, you have 0 pressure. That's what we call absolute pressure, but we don't measure, just like temperature, we don't measure everything using absolute temperature, right? We also measure things using relative temperature. For example, Celsius temperature is relative to freezing point of water. Fahrenheit temperature is relative to the freezing point of some salt solution, right? Those are relative. And so the same thing happens with pressure. Sometimes we measure the absolute pressure, where if there are no collisions, there's no pressure. However, there are times when we register the relative pressure when we get 0 pressure, but there's still pressure in there. There's still pressure. That's, we give a name to those things. The absolute pressure is just called the absolute pressure. The relative pressure is called the gauge pressure, which we'll talk about in a minute. Anyway, they're going to be collisions, and that's actually, we don't need all these details. There's a lot of details in here. We can just ignore all these. How do we measure pressure? Have you guys used the triple beam balance? You guys use the triple beam balance in the lab? Triple beam balance is like this. On one side, you put the ream of paper. On the other side, you put a whole bunch of masses, right, until it's balanced like this. This is a mercury barometer. A mercury barometer works like a triple beam balance. It works like a triple beam balance because on one side, the outside here, you put the weight of the atmosphere. On the inside here, you put mercury. Now, what is the density of mercury? Density of lead, does anybody remember? The density of gold is about what? About 20. The density of lead is about half that, right? Around 11. The density of mercury is like lead. Mercury is like lead. In fact, mercury is more dense than lead. Mercury is like 13. In other words, mercury is like 13 times more dense than water. 13 times more dense than water. So think about, if you were swimming in a swimming pool of mercury versus a swimming pool of water, one, you probably couldn't sink in the mercury because it's too dense. But let's say you put some weights on you, gold weights on you. If you put gold weights on you, you'd be able to sink in mercury, probably. If you're swimming 30 feet underwater, you got all that weight, 30 feet of water above you, you're going to feel that pressure, right? If you were swimming in a mercury swimming pool, you'd only be swimming in 3/4 of a meter of mercury to have that same weight. You know? And so about 30 feet of water is what we call 1 atmosphere of water. Plus the 1 atmosphere of lead gives you 2 atmospheres of total pressure. It's going to be way high pressure. If you're swimming in a mercury swimming pool, you'd only be swimming in like 3/4 of a meter deep, and you'd have 2 atmospheres of pressure on your body. And you'd feel that. You know, we don't feel 1 atmosphere. 1 atmosphere is a lot, you know. 1 atmosphere is a lot. We don't feel it because we're built to live in a 1 atmosphere environment. We'd feel it a lot if that 1 atmosphere were gone, you know, and we were in a vacuum. We'd feel extreme pain. And so what we do is we have this is called a barometer. A barometer is you weigh, okay, on the outside here is the weight of the air. And it doesn't seem like air weighs much, but it weighs a lot. In fact, air, in order to balance out, you know, it's going to push up the mercury up here. And so this weight of mercury here is the same weight in air. I have some liquid mercury. over there if you want to feel how heavy this stuff is. It's extremely heavy for a small container. And so this is like a triple beam balance. This is how we measure it. And so some days the atmospheric pressure is a little less. If it's a little less, then what's going to happen is some of this will drain out, so that we get equivalent weights. And so in other words, we're doing this. The air pressure here is the same as the liquid pressure here. At this level, it's balanced. We're properly balanced. This. If the air pressure were greater than this, then it's going to push up more mercury in here. If the air pressure goes less, then some mercury is going to drain out here. All right, now we can use some physics to figure out the pressure of a liquid. There's an equation for that, an empirical equation for that. The pressure of a liquid is equal to the density of the liquid times the gravitational constant, G. You recall seeing that? You don't have to, because we aren't going to do any calculations with G. But G is 9.8 meters per second times the height. And so the gravitational constant is a constant. So it doesn't change unless we go, The density of mercury, does that change, or is that fairly constant? It's fairly constant. So the only thing that changes in that equation is the height. And so rather than calculating, because it's a hassle punching in the buttons and calculating the actual pressure, rather than calculating the pressure, instead we just take the height as being directly proportional to the pressure. And so however tall this is, it's like 30 feet of water. What's the pressure? Well, I don't want to calculate it. I'm just going to say it's the pressure at 30 feet of water. If I'm at 60 feet underwater, it's a lot higher pressure, right? It's going to be a lot higher pressure. Will it be double? If you go 60 feet underwater, will it be double? Well, that's what we need to know. We need to know what that empirical equation looks like. Is it linear or is it non-linear? If it's linear, it would double. So 60 feet would double, 90 feet would triple. Or is it non-linear? And obviously, if we knew the theory very well, we can figure it out. But we don't need the theory. We can just take some observations and come up with an equation and try to model it. It's fine. But anyway, what we do here is rather than hassling with calculating the actual pressure, we just measure how tall this is. This is, when we look on a normal day at sea level, this is 760 millimeters tall, 3/4 of a meter tall. That's that's what we call 1 atmosphere pressure. And so that's a mercury barometer. Mercury barometer. Yeah.
So does that mean 760 milligrams of mercury in 1 atmosphere are all equal?
It's not it's millimeters here. Yeah, 760. I'll tell you what's all equal. 760. You'll hear inches of mercury on the weather. Have you heard of inches of mercury on the weather? So 760. These are. We call it 1 atmosphere. 1 atmosphere is 760 millimeters of mercury height. This is liquid mercury, which is 760 divided by 25.4. This is 29.87 inches. 29.874, etc. inches of mercury. This is not exact. This is exact. This is approximate. Which is equal to, 760 torr. This is named after Torricelli, who's one of the pioneering scientists with this kind of gas stuff. So sometimes you'll hear torr, sometimes you'll hear millimeters of mercury. Most of the time you'll hear millimeters of mercury, though. What is this equivalent to in water? Water is a lot less dense than mercury, so it weighs a lot less. So we need a lot more water to compensate. And so I forgot the exact density of mercury. I'm not thinking, density. mercury. Let's take a look at mercury. Mercury is an unusual metal. Mercury is the only metal that's a liquid. This is it here. Does mercury like glass? Mercury hates glass. Look at it. You know, mercury's trying to avoid touching the glass here. This is why. You see how, you know, water would just spread out. Mercury doesn't want to spread out. Mercury wants to stay with mercury. In other words, the mercury atoms themselves are really sticky. And it depends on the stickiness of the glass, you know, so which one's more sticky. Mercury is more sticky than mercury to glass. That's why. This. In fact, there's something pretty amazing. I don't know if you've seen the mercury sphere. You know, let me see if I can get an image of the mercury sphere, because I just thought of that. I've been thinking about that earlier. But there's one image in your book. I didn't bring your book. So, but there's one image of a ball of mercury like that. I mean, you know, it has to fight gravity, of course, but it hates this mercury hates this surface so much that it, you know, in order to minimize the contact, it forms a ball like this, so that the contact with the surface is, yeah, at the absolute lowest. So you can see these are called beads. And these beads roll around and they're very hard to deal with and clean up. All right. Anyway, let's go on here. So normally when we're thinking about gases, we want to know the pressure of the gas. You know? Now, the pressure can be higher or lower depending on, you know, how many molecules or atoms or ions are in a given volume. Temperature also can affect pressure, etc. So typically we want to know the pressure. We also want to know the volume of the gas, the amount, you know, how many particles there are, and the temperature. Those we'll talk about more detail. You don't really have to write this down. Now, the pressure units, you know, we deal with atmospheres typically. It's a unit of pressure based on sea level at the equator. And it's capable of supporting a mercury column 760 millimeters high. And that's one. So this is by definition, I think, 1 atmosphere. Pretty much exact. It is exact. A torr is the same thing as a millimeter of mercury. So 760 millimeters is the same thing as 760 torr. A Pascal. Now Pascal is the actual physics of this. When you have collisions like this, it exerts a force of the collision. That force is measured in physics units. Newtons, have you heard of Newtons, after Isaac Newton? And so we're looking at Newtons over a certain unit of area. So Pascals are Newtons per meter squared, you know. But this is the actual physics of the collision. And so when we're looking at this, 1 atmosphere is 101,345,000 pascals. And so pascals is the you know, Pascal is like the metric system, unit of pressure, and atmospheres is like the English, you know, the U.S. system and that kind of thing. Although England's switching Pascals. Well, one bar is, actually this is pretty much the agreed upon standard now. In the US, they're trying to switch from atmospheres to bars. Fortunately, atmospheres and bars are very similar. And so the pressure is about 1 atmosphere in atmospheres, and the pressure will be 1 bar, roughly, in bar. 1 bar is equivalent to 100 kilopascals or 100,000 pascals. So a bar and an atmosphere are very close. We also have pounds per square inch. In terms of PSI, or pounds per square inch, 1 atmosphere is equivalent to 14.70 PSI. And you feel that, 14.70 pounds per square inch, you can feel that. Which ones do you have to have memorized? Pretty much this. Right there. That's about it. All right. We have the barometer. Another device very similar to a barometer is called a manometer. And we'll talk about the manometer. We'll go on a break. We'll talk about the manometer in a minute.